This instructional video is intended to show you the three-step process for going from a reaction velocity expression to an integrated rate law. And those three steps are separate, integrate, and linearize. So let's write a sample of a reaction velocity. So it's always the change in concentration over time. And because we're making it an inequality, it's going to be equal to some rate constant times the concentration raised to the actual order of your reaction. So depending on whether it's a reactant or a product will determine what the sign is. So if it's a product, the sign will be positive because the products are appearing. If it's a reactant, the sign will be negative because the reactants are disappearing. So let's do this for a reactant. So step one is to separate. So we want to have everything that has variables of concentration on one side. We'll keep the rate constant for disappearance because we're talking about a reactant, and have that with time. So we've done the separation, so now all we need to do is integrate. For the integration, you're always going to integrate from time 0, so the original concentration, to time t. And so from time 0 to time t as well. So once we solve that integration, we can then linearize it. So let's look at what happens for a zero order reaction. If n equals 0, then it's just integral of dA. So integral of dA is just going to be the A concentration, which means that we have A concentration at time t minus A concentration at time 0, and a minus kT. So to linearize that, this is the variable that's changing, so that's like y, mx plus b. So for our zero order reaction, we see that this then states that we start out with an initial concentration at time 0. Each time we increase the amount of time, we are subtracting some out, and that's what gives us the current amount of our concentration. So let's look at one more for a first order reaction. So in this case, our exponent is 1. So we end up with the integral of dA over A. If you know your calculus, that's the same as dx over x, which is just going to integrate to ln of x. So we're going to have the natural log of our concentration at time t minus the natural log of our concentration at time 0. Again, this is going to integrate to minus kT. And if we want to linearize, meaning we want it to look like y equals mx plus b, then we get the natural log of our concentration at time t equals minus kT plus the natural log of our concentration at time 0. And so in both of these cases, what we see, let's do it for highlights, for that linearized step is y equals mx plus b. What that means when we take step 3 and linearize it is that this gives us a way of understanding how best to plot it to see the linear relationship between things and extract a value for our rate constant. For a zero order reaction, our x-axis is time and our y-axis is the concentration. For this first order reaction, we're going to have, let me just put that t there. So for the first order reaction, you're going to have For your x-axis, time, and for the y-axis, the natural log of the concentration of that reactant. But this is the effective start of doing integrated rate laws, recognizing that we separate. So we go from our reaction velocity to separated variables. We're going to do the integration. And when we have a specific value for that exponent, that order of the reaction, we can then complete the integration and linearize everything out.